Welcome to the fourth episode of my little Haskell Screencast series. In the last one we looked at cyclic infinite lists. These are lists that are fully evaluated but still fit into memory because they happen to be cyclic, and how functions like map, if you apply them to such lists, break this property. And we're wondering, is there maybe a way to write a map function that does not break that property, where the output is cyclic if the input is cyclic? So let's recap first the problem. So here we have GHEI. I'm defining a cyclic list ABC, D, and now I can evaluate it. It's very large, it's nice. And I can look at it in GHEvis. There we go. So this is a cyclic list, and because it points to itself, it's fully validated but doesn't need more space than these 4 cells. But if I now try to map a function, so here's a definition, over that list, and maybe I look at the first 6 elements and I look at the memory representation of that, I notice that it's actually grown. So it has now 1, 2, 3, 4, 5, 6 const cells. And if I evaluate more of it, it'll just grow. Because it doesn't know that the input was cyclic, and map just always produces a non-cyclic list. Could it do differently? Not really. So in pure Haskell, you have no way of distinguishing different values that happen to have different representations, cyclic versus non-cyclic, if they denote the same value. And all of these just denote lists, and you can't tell what they made of in pure Haskell. But we don't have to stay in pure Haskell. GHE provides a bunch of unsafe features for low-level programming, and they are used in bindings for foreign function interface libraries, or also in tools like the one we're looking at here, GHEvis, which is using a bunch of these unsafe features to inspect the memory. So if this tool can visualize an infinite list, maybe we can write a map function that also preserves this property of infinite lists, infinite cyclic lists. So I gave it a try, and I wrote a cycle map module that contains a CMap function that tries to preserve the cyclicity of the input given a map function, or given a function to map over it. So the definition of map is more or less the standard definition of mapping a function f over a list. So you might recognize this part here. It's only written with a fixed point combinator. A fixed point combinator tends to have a type signature like this. So it produces a function a to b if you give it an a to b, and you use the argument, which is the same as the recurse here or here, whenever you do a recursive call. So here we map this function f over the list by saying if the list is non-empty, we apply f to the element, and then we continue with this recurse function here. And to implement this memofix function, now we reach for unsafe features. So here we have unsafePerformIO, which takes an I/O action, stuff that can do printing to the command line, store I/O refs, could even open the network connection, and hides it inside a pure value, so that only when that pure value is needed, the I/O action will run, and then can do I/O stuff. Eventually, the result of that I/O action becomes the value of that pure value. We use this here to be able to create an I/O ref, a mutable variable that we can update during our code. And in this variable, we store a list, which is a lookup table. So a list of pairs, and we can see that down here. So in fact, the function that we're producing, before it does anything interesting with specific with it, it looks at the argument and gets a stable name for that. A stable name is a bit like a pointer, but in GHC, the runtime is free to move around things in memory. It has a copy and garbage collector, so it needs to copy things to other places. Therefore, pointers are not stable, and you might not recognize something just by remembering its pointer from previously. But stable names solve the problem. They are updated by the runtime whenever some object moves, so that you can still compare them for equality and recognize objects you've seen before. So we take the stable name of the argument, we look in the table, and see, have we seen this particular object before? And if we have, we just return the value that we remembered. And if we haven't, we now have to add an entry to the table. So we apply f to x to calculate the result, and we store the result together with the stable name in that table. And then we return the result as well. And here it's very important that this is lazy. So f will not actually run until something needs it. We don't need it here. Therefore, we can add this entry to the table before anything else runs. Which means that even if the execution of f on x will maybe need that value, because it's a recursive cyclic thing, it will find it there by the time we evaluate the result. So does this actually work? Well, we can define L2 again, but now we use CMap, which we have to, of course, load. So L2, now L is infinite, but nothing changed here. L2 also looks infinite, but is it also cyclic? Well, let's have a look. Here's L, and here's L2. Perfect. L2 looks just like L. It only has 4 cons cells. It is cyclic. It has the thing we want. So just to wrap up, let's look a little bit. What does CMap look like in memory when it's partly evaluated? So let's define L2 again. Let's look at the first 2 elements of L2. And then we want to look at L and L2. And this is now more complicated than the normal map because it does all this bookkeep. And we can see it here. So L2 is A and B, followed by a thunk, because we haven't looked further. And that thunk refers to a bunch of things, in particular an stref and a mutva, which is the IOREF, pointing to a list of pairs. This is the memo table that we created. The first element is always a stable name. And the second element points to, well, let's see, L2, which makes sense. One of the results of the function that we're memorizing, the map function, is L2. And another result of another recursive call was the tail of L2. And if we now continue looking at L2, let's go to the end. So now we have evaluated 4 elements. So we have A, B, C, D. And this thunk refers to a memo table with 4 elements. So we have these 4 pairs. And they refer to the output list, to the list that is L2. And then in the next step, the thunk will look at the original input list, L, will notice that the stable name of L is one that we've already seen in our table. It's probably going to be this one. So it will use the stored result rather than just recomputing and going on. And the stored result for that input is L2. So once we evaluate that, we will have the nice cyclic data structure. And there we go. So this is how you could define a map function that preserves cyclicity. But you shouldn't use this in practice. Clearly, this map function is horrible algorithmic complexity because for every new recursive call, it goes through the whole list of previous ones to see if you've seen it. And even if you could optimize it a little bit, it's still going to be very expensive if maybe you're using it on a large list that isn't even cyclic. So really, if you feel the need to reach for something like this in a more realistic program and not just playing around like here, then maybe you need to restructure your code. And maybe cyclic data structures aren't the right idiom for what you're trying to do. But I hope you still like this little experiment and this little playing around with unsafe features, and hope you learned a little bit. If you want to learn more like this, just comment with ideas you have, and maybe we can have more episodes of this. Thank you. Goodbye. See you next time.